Hello everyone, this is Xiaoying. I'm here to present our work towards self-learning end-to-end task-oriented dialogue systems. First, I'd like to talk about the motivation. End-to-end task boats are typically learned over a static and usually limited size corpus. However, after being deployed in changing environments, task boats tend to fail when confronted with data that deviate from the training corpus. Changing environments are quite common and arise from unseen user behaviors and task definition extensions, where the first refers to unseen language patterns and unknown user goals. For example, user may query carefully about address. The second is related to new functions or new tasks. For example, a restaurant bot designed for the table booking service may also encounter queries about delivery service after deployment. So how to enable task bots to adapt to changing environments? Intuitively leverage the accumulated human-bot interactions which contain useful information. When the user queries carefully about address, the bot fails to provide it at first, but gives it in the third response when user queries in a detailed way. However, the interactions are labeled, then how to leverage them. Previous approaches thinking for human annotation never realize there are some limitations. In this work, we propose a new research problem, how to enable task bots to automatically adapt themselves to changing environments by learning from the interactions with minimum or zero human annotations. And we propose a self-learning framework, which contains a data model for generating responses and the pre-trained reward model for judging the quality of agent responses and outputting reward scores. The framework operates in the following steps. First, the bot is trained with the available label dialogues. Then the bot is deployed online to converse with users and accumulate and label human bot dialogues. Then dialogue model is refined with the logs via reinforcement learning using the reward scores. Here's the illustration of the refining procedure. In this way, the bot can automatically adapt to unseen user behaviors without extra human annotations. Regarding the extensions in text definitions, machine teaching is utilized to provide necessary instructions on how to handle new functions. After that, the bot quickly adapts to new functions through the self-learning procedure. Now we talk about dialogue model. Here we employ Solist for demonstration, which is an autoregressive end-to-end dialogue model. It generates responses based on the dialogue history, generated belief state, and fetched DB state. However, they suffer from unseen user goals and slot values. Therefore, we propose to synthesize dialog examples through exhausting DB values and replacing the entity knowledge in user goals, in addition to special tokens in the utterance. Then the reward model, essentially it is binary classifier. It takes dialog history, belief state, DB set, and response as input and output a reward score. Specifically, we devise a data augmentation strategy to construct positive and negative examples based on the given dialog training corpus. We consider 2 kinds of positive examples and 5 tests of negative examples. To boost the performance, we're following the pre-training and fine-tuning paradigm. The framework is based on the reinforced algorithm for adapting to new tasks. Machine teaching is utilized to provide necessary annotations by correcting representative failed dialogues. In the experiments, we studied 2 questions. We used a single data set organized from multi-words. Here are some compared methods. To verify the effectiveness of the framework, we construct 2 settings. Setting 1, unseen user behaviors. We use the simulated human bot dialog logs for either reproduction. The table represents the end-to-end evaluation results on 4 tasks. Satisfy is trained with 5 labeled dialogues randomly sampled from the training set, which is a standard baseline. So S is trained using the synthetic dialogues constructed from the 5 labeled dialogues using synthetic dialog construction, which shows the effectiveness of the proposed synthetic dialog construction for identifying user behaviors with unseen slot values. The third is the data augmentation baseline. SLA Solist is refined based on Solist S using SL agent, while the results demonstrates the higher efficiency of directly learning from the human bot dialog logs. Solist OA is refined using the online active reward model. So the stage is refined using the query return level human feedback score. This shows the strong capability of turn-level opportunity reward model for judging the quality of responses. Further, we conduct experiments with real human-bot dialogues. The results are consistent with simulation evaluation results. Then the second setting, we follow the domain extension experiment setting by introducing new slots and DB values. The second refers to the result of machine teaching, which is trained with 10 annotated dialogues obtained through machine teaching based on list S. The result exhibits the effectiveness of machine teaching for handling new functions. Then it is deployed and refined using SL agent. It shows that enhanced by machine teaching. So SL agent enables flexible adaptations to new tasks. Furthermore, we conduct human evaluations. Obviously, the results are consistent with automatic evaluation results. Here are two interactive examples. Finally, the conclusion. First, we propose a research problem. Second, a self-learning framework. Thank you.